want to talk a little bit about this 2 times C2, C1, all of this stuff that's going on here. This piece that is not necessarily the focus of our solution because it's just the constants, it's just the arbitrary constants, but we can get confused by this if we focus too much on this. What this is really saying is we have some unknown object, C2, and we subtract some other completely unknown thing from it, C1. We multiply by 2, and all we're going to end up with is something else that we don't know. So rather than carry around all these different C values, all these different constants that really don't mean anything, what I'm going to do is I'm just going to call this C. All of this together is just going to give me some other number, and however I choose to express that number, there's really only one constant in any particular problem. There's really only one constant, and that simply affects the vertical shift of that particular function. But we end up with y squared now equals 2/3 x cubed plus our constant. So if we go ahead and take a look at what the results are here, the next thing I may choose to do is to square root. So we end up with y will equal plus or minus the square root of 2/3 x cubed plus a constant. And this will be now our solution, and the size of C again will be determined by our initial value problem in this particular case. But this is a separable differential equation. We have gone through and we have solved it by separating out and putting the y dependence on one side, the x dependence on another, and integrating the left and right hand sides, and then doing some work to simplify this. One of your assignments, one of the things I would like to have you do is take this particular expression and find dy dx and verify that it satisfies the differential equation that we had above. So please verify that this satisfies dy dx is equal to x squared divided by y. Please take and verify that the differential equation that we started with is in fact solved by this solution that we have determined here. Well, that's a good introduction to the concept of separable differential equations. What we're most interested in today, in terms of focusing on applications of this and understanding just exactly how these work, I want us to focus on a particular kind of differential equation here. And this differential equation looks like this dy dt is equal to k times y. And in this particular case, we're talking about a k value that represents a growth or decay constant. So the sign of this tells us whether the function is growing or if it's decreasing. And that should make perfect sense to you, because over here we have the slope, we have the rate of change of this function. We have the rate of change of this function. So clearly if the constant k is negative, the function is decreasing, and if the function is increasing, that must mean that k is positive. So this k value determines whether our function is increasing or decreasing. We have actually taken a look at the slope fields for this particular problem. I would encourage you to go back and look at that discussion, or back into your notes if you would like to take a look at those. But a good way of interpreting this particular differential equation is that it simply says that the rate of change is proportional to the current value. Okay, the rate of change here is proportional to the current value. We have the rate of change is proportional to the current value. It depends on how much we already have. Okay, so the more you have, the greater the change. This is a good way of thinking about what this differential equation says. The more you have, the larger the change. Okay. Take a look at this differential equation for a moment. Is it separable? Is this a separable differential equation? Can we separate out the x and the y components, those dependencies? Can we separate those out into two separate factors? Since there's no x dependence on the right-hand side, this is certainly a separable differential equation. And when we go to separate this, dy dt equals ky, what we're going to be able to go through and do here is simply move the y over to the left-hand side. We can do that by multiplying both sides by 1 over y. And we can also move the dt, this differential dt over. And what we find is the differential equation can be rewritten as 1 over y dy is equal to a constant times dt. We now have separated this differential equation, and we will work to find the solution here by integrating. If we know the antiderivatives of the left and right hand sides, we can solve this equation. So we're going to integrate the left hand side, we're going to integrate the right hand side. The integral of 1 over a variable is simply the natural logarithm of the absolute value of that variable. And again, we'll go ahead and throw in our plus c here, plus a constant. The right-hand side is the integral of some constant times dt. If you'd like, we can move this constant out. We just have the integral of dt. And what this simply says is, what is the antiderivative of 1? What do we have to start with in order to have a derivative of 1? And the answer here is fairly straightforward. We end up with the expression, the natural logarithm of the absolute value of y plus a constant is equal to k times t, because the derivative of t with respect to t is simply 1. Just as before, one of the things we would like to do is we would like to rewrite this expression so that it is written as a function y equals. Let's go ahead and do that. We move the constant over, so minus c. Notice that I didn't put in a constant here. Notice I should have, in theory, I should have made sure that I had a plus constant on the left and the right hand sides. However, in this particular case, I know that I already have one constant in here, and it's simply going to get moved over. We're going to collect all the constants together. So at the end of the day, I'm just going to have a constant. And if we look at this, we end up with the natural logarithm of the absolute value of y is equal to kt plus some constant. Now the constant might be positive or negative. We don't know the sign, we don't know the size. That's okay. We know that we have one arbitrary constant in here, though, that we don't know exactly what that is yet. And the next thing we want to do in order to solve this problem is to take the anti-natural logarithm of both sides. So our function will now look something like this. E to the natural logarithm of the absolute value of y. And of course, e and natural logarithm, or the anti-log, and log are inverses of one another. We end up with just y on the left-hand side. And we end up with e to the kt plus c. This is getting to a point where it should look familiar to you from, again, Algebra 2 and pre-calculus. I'm going to use a property of exponentials to rewrite the right-hand side. If I have the power of a sum, that becomes the product of the individual pieces raised to different powers. Okay, and so this is a good expression to finally describe as an exponential growth or decay equation. So notice where exponential growth and decay come from. Exponential growth and decay come from the fact that if the change in a substance, the change in an amount, depends on how much you already have, in this particular way we end up with exponential growth. I want to do one last thing, and that is I want to focus on what this e to the c represents. So what we're going to do is we're going to assume that y is equal to y initial at t equals 0, and this will give a very clear interpretation of our constant in this particular problem. What we find if we plug this in is that y will equal y0, and that comes about by plugging in 0 for t. And of course, e to the 0 power here will simply be 1, which tells me that this y initial value is exactly what our e to the c, what this constant is here. And so now we can rewrite this in a way that is more familiar to you. We can say that the amount we have at time t is equal to the initial amount times e to the kt, where k again is our growth factor. Okay, this is a very important equation for describing many different kinds of relationships, whether it's in biology, in physics, in chemistry, in finance, and banking. This is something that shows up in many different situations. So I'm hoping that this has clarified some of the issues for you that you may have been experiencing in looking at lesson 6.4. This is the last section that we will be looking at. In this particular chapter, we will not be covering logistic growth. It's very interesting. I would encourage you to look at that. What it does is it takes the exponential equations that we have been focusing on and it makes them slightly more realistic. If you think about one of the classic descriptors or one of the classic models that we discuss when we talk about exponential growth, we talk about bunnies having babies. We start with 2 bunnies and we end up with 4 bunnies and 8 bunnies and we end up with exponential growth. That's not purely realistic when you think about the fact that any set of bunnies is going to have a finite area to live in, and so there's sort of a maximum population. Our equation, the exponential equation here, does not account for that, and if we use this as a model, this would predict larger and larger and larger populations of rabbits extending off into an infinite number of rabbits, which of course is completely impossible and very inconvenient. So what we would rather do here is focus on a model that involves a maximum population value. The logistic growth equation takes that into account. So we are done with this chapter, and our next chapter will begin to focus on applications of integrals. It's a very short chapter, but it is a very dense chapter. I anticipate it will take us 2 to 3 weeks to cover the material in there. Almost certainly many of the ideas in this particular chapter, chapter 7, will be covered within the AP test. Once we have finished chapter 7, we'll touch on a few topics that are of key use in solving some things we already know how to do related to limits, and then we will begin our formal practice of the AP test. We'll go through several practice tests, we'll pick them apart, and we will do everything we can in class to make sure that you are prepared. So again, if you could, for tomorrow, please make sure that you have determined the derivative of our y-valued function that we determined was the solution to that differential equation, and show that that is actually a solution. I will be looking for that at the start of class tomorrow.